Hello all and welcome back to this course on digital systems. In this week, we started looking at the idea of Karnaugh Maps, and we started with 2 variable, 3 variable, and we were discussing the 4 variable Karnaugh map, right? So one other interesting case that we can throw into this KMap solution is the idea of a don't care. Okay, so let us consider the following. Okay, there is a case here. Basically, we are saying that this has 4 inputs. Okay, A0, A1, A2 and A3. This is a black box. Right? Now, what do? We are going to say that let us say the following. Okay, from outside I am going to impose a certain constraint on this. Okay, I am going to say my control from outside is B1, B0, B1, B2. So I am going to say the following: A0 equal to B0, okay, A1 equal to B1, A2 equal to B2, but A3 is B2 bar. So in some sense, what we are saying is the 4 inputs A0 to A3 to the black box are not independent inputs, right? So in some sense, we don't have to worry about the conditions of all 16 combinations, okay, and this will allow us to simplify the truth table significantly and get a much simpler Boolean implementation for this particular problem. So let us consider this case. Let's say I have A3, A2, A1, A0, right? Now, for simplicity, let me consider there is only one output. Why not? Okay, and I am saying 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1. And now I will make a copy of this as usual. Okay, yeah, and I have the last input which is 1, 1, 1. Obviously, I am going to now replace the MSB with 1, 1, 1, 1, 1 and 1. Okay. So let us consider this case where we did not have this particular external constraint where B, A2 and A3 are necessarily complements of each other. Okay. So if that were the case, right, then essentially let's say I had a truth table which was the following: 0, 0, and then let me say 0, and okay, then I say 1, 1, 1, okay, and I say 0 here, 1, 1, 1, 0, and I can say 0, 0, 0, 0 here. Okay, I am just arbitrarily picking some sort of a an expression like this. Okay, so what I'll do is let me go back and just copy this truth table, I mean this whole KMap again, so that we are able to implement it and see for ourselves. Okay, so let me first erase all this because it's not relevant to this problem. Okay, so effectively what I have here is the min term 0, 1, 2, 3. So this is M4, M5, M6, M8, M9, M10, and yeah, so it is f of A3, A2, A1, A0. Okay, I am just writing it in that order, is sum of products 4, 5, 6, 8, 9, 10. Right. So, we have 4, 5, 6, 8, 9, 10. 6, 8, 9, 10. Okay. Now, this is not very obvious, right, of how to simplify. So, one thing that we can do is obviously this, right. So, I can write my f of A3 to A0. Okay, let me write that explicitly. A2, A1, A0 equals I will just say it is A bar B, okay, in magenta, A bar B into C bar, because C bar is not changing for the magenta, right. Then I have in orange, I can do this, right, and therefore write this as A bar B into D bar, okay. Then I can do the same thing on the row below, okay, which is going to give me plus A B bar into C bar, okay. And finally, I can do this and get the last term, which is A bar B into A B bar into D bar, right. So, if you look at this, this is basically just grouping it. It seems to be some C bar into A XOR B plus D bar into A XOR B, right. So, it is A XOR B into C bar plus D bar or something like this, or CD whole bar, whatever, right. So, let us just leave it like that for now, right. But what is interesting is, in this particular example, we have forced this black box, right, to have a certain implementation, assuming that A0 to A3 are all independent of each other. But now, what if I completely ignored the case, because I know from outside B2 is connected to A2 and B2 bar is connected to A3. This is given, right, the way I am using this black box, okay. Therefore, there is no way that A2 and A3 can actually take the same value. They have to be complements of each other, right. So, in some sense, what we are saying is, we have imposed these, you see these zeros here, that is actually complicating the entire thing. Why? Because in all these cases, in these 4 cases, A3 is equal to A2, but we know that this condition is never going to occur from outside, right. Likewise, when you look at these 4 conditions, simply observe here, A3 and A2 are again the same, equal to 1, and we know that can never occur. So, when we are trying to design such a circuit, and we know that A2 and A3 are independent of, are sort of dependent on each other, we could use the following case, right. Instead of saying zeros here, right, or maybe I will not say that, I'll leave that. I will have another thing for Y1, right, and I will simply put a new truth table, don't care, right. It means I don't care what my output Y1 is, okay. Let us say this is Y1, okay. I don't care what Y1 is if A3 and A2 are the same, because I know that condition is invalid for that particular use case, okay. Of course, the same black box could be used elsewhere where A2 and A3 might be independent. In that case, this will not hold. There we do care for what the outputs are, right. But then I say, okay, 1, 1, 1, 0, 1, 1, 1, 0, and then I say don't care, don't care, don't care, and don't care, right? So in some sense what we are saying is the following, okay? We are saying that the evaluation of y1 is now going to be slightly different. So let me remove all this. The ones I can retain because that is the same for y1. So y1 is summation exactly the same thing actually, right? If you look at it, it is 4, 4, 5, 6, 8, 9 and 10, but I am also saying one additional thing, that for the other inputs, right, for which ones? For min terms M0, M1, M2, M3, they are all don't care conditions. So you see this, I am saying, let me put that in a different color in purple. These are specifically don't care conditions. That is when A is what are we saying now? Oh, by the way, sorry, I should not have used this thing, right? Okay, this whole thing is being done with respect to A, B, C, D rather than A3 to okay. So I have to make the following mapping here. A3, otherwise the whole thing will fall apart. A3 equal to A, A2 equal to B, A1 equal to C and A0 equal to D. Essentially this is the the mapping that we are doing, right? And even when the A and B are the same, right, we are saying this is the truth table. Okay, so what this is allowing us to do now is something very, very interesting, right? It's basically telling us that I can treat this don't care as either 0 or 1 as per my convenience, right? It does not mean that making everything 1 is a useful thing to do there, right? No, we are just saying it makes sense to treat each x independently as a 1 or a 0 depending on our truth table, depending on the Boolean simplification that is allowed. Okay, for example, this is very clear. It allows us to do a grouping of 8 like this, which means the whole AB is gone, right? So we are now talking about y1 equals simply it actually only is C bar, because AB is out of the equation. Going from the 0 to 1 min term, it's only C bar that remains constant, right? C bar, and then we also have the second term which is here. Plus or we are saying or C D bar, right? In fact, we have, this indicates something very interesting to us. You look at this, it allows further simplification because this grouping is not the most optimum. The grouping that we should have done is actually the following, right? If you group it like this, then this term will simply become, going from this thing, it will become D bar, right? So what we have basically said is, we have gone and replaced all these terms, okay? Let me put that in green, okay, with 1, right? This we are treating as 1, okay, even this one. However, these two don't cares we are treating as 0. Remember, if you had put a 1 here, right, it would have complicated the thing, because if, for example, if this had been 1, this could have also been 1, right? It's still an equivalent implementation of that, because it's still an invalid case as far as that use case is concerned, right? But that would simply complicate the expression, because I need to now do these two. implement these two, and this simply complicates my implementation, and therefore it is better to treat this as 0. So the green and blue ones and zeros are actually our choice. We are simply saying I don't care what the output is in such an implementation, as long as I don't care what the output on y1 is, because I know that the input a2 and a3 are complements of each other as imposed by the use case from outside. Okay, so that's why if you come here and see, by the way, if you see this implementation here, right, we are going to simply say the following. We are going to say f of a, b, c, d, right, is going to be, so you look at this, I will combine these two and I will combine these two, right. I'm going to combine these terms. So you will get C bar into A bar B plus A B bar, right. And then we said plus D bar into the same thing, that is A bar B plus A B bar, right. And therefore this can be written as A bar B plus A B bar into C bar plus D bar, right. But what are we saying? A and B, which are basically A3 and A2, are complements of each other, and therefore this A XOR B, right, this is nothing but A XOR B, by the way, right, into C bar plus D bar is essentially A XOR B is always 1, because I know they are both complements of each other from as determined from outside, and therefore this will reduce, if you impose that condition from outside, this will reduce to C bar plus D bar if A equal to B bar, right. And that's exactly what you got here by imposing that particular don't care condition, right. So this is the beauty of using a don't care condition. Just look at it. It has simply brought this. Now what is C bar plus D bar, by the way? You can simplify this even further and make it C into D whole bar by De Morgan's laws. Actually this is nothing but a NAND gate with inputs C and D y1. On the other hand, just imagine the complexity of implementing this particular case. You need an XOR gate. So let's assume that you have an XOR gate. Then I can write this as A XOR B and C D whole bar. So effectively, right, I have C and D, I get the NOR, right. Then I have A XOR B like this, right, and then I am going to AND these two, and I will get y0 as my output. This is y0. On other hand, this is y1. So clearly you can see that y1 is actually a subset of this implementation. This is y1. This whole A XOR B followed by the AND gate is completely unnecessary from the implementation point of view if that don't care condition is used appropriately, right. And that's the that's how effective don't care conditions are, right. And this will come in handy in many cases, right. This is just what I've shown you here is just a single use case, and to summarize again, it's not that every don't care has to be as 1 that or 0. No, you choose as per your convenience, right, and that is what you are going to implement. So if you implement CD whole bar, right, you will have the case when C and D happen to be 1, you will have the case that the output actually goes to 0 instead of a 1, right. Yeah. So with that, we wind up the discussion on the KMaps, 2 variable, 3 variable and 4 variable. The 5 variable is doable on paper, but it is still not I would say it's more very academic theoretical exercise. So we are not going to get into 5 variable KMaps. Beyond 5 variables, 6, 7, 8, and you basically cannot represent it on a 2-dimensional paper plane easily, right? That's why it becomes complex. And therefore, also it is definitely true that today's circuits have, like, thousands of inputs, right? So this idea of trying to use a K-map to simplify is not a scalable technique that can be used for arbitrary circuits in practice. In order to do that, you need algorithms, computer algorithms that will actually sort of, maybe take a truth table or a Boolean expression and sort of simplify it using certain, greedy algorithms and give you as simple an implementation as possible, right? This is completely beyond the scope of this particular course, and therefore I am not going to get into that detail right now in this discussion. So with that, we can wind up our discussion on the K-maps. Please do practice enough problems on the 2, 3 and 4 variable K-maps, because this is the best way for you to get comfortable with the laws of Boolean algebra as well. Thank you.